Hello, everyone, and welcome to my channel. This is Sohini from South Bay, California, and I welcome you today. For anyone who's tuning in for the first time, this is where we talk about everything AI, computer vision, natural language processing, so on and so forth. We learn new technologies, and we cover research material, and we also do small coding exercises. So welcome. So today, I wanted to talk about a recent paper that I've been able to successfully publish in IEEE IJCNN. So for anybody who's interested in figuring out methods in order to annotate and store and retrieve video files and also be able to annotate per frame, this would be the video for you. So think about what happens whenever we have video sequences. Video is just, a collection of images. But whenever you have to annotate them, you have to think about which ones are really the frames that you should go after. If you're looking at sequences, most of the sequences in consecution are going to look very similar to one another. So finding the key frames that you should extract and annotate can be an extremely manual and laborious task. So today, this paper will show you how to automatically generate metadata about a whole video, how to store it very effectively, and also two methods in order to extract these keyframes that you should then, pass for, annotation. For instance, if you are doing object detection, so maybe you already have a pre-built object detector, but now you want the pedestrian, detection to be even further improved. So in that case, you will now have a method to very quickly find out the images that have more pedestrians or that are having more errors because there are more pedestrians lying in them. And then you can quickly, extract them out using these methods that I'm talking about. And these are all semi-supervised or unsupervised methods in order to then annotate them and make your model, which is your pedestrian detection in this case, even better. So if this is of interest to you, please subscribe and like and share this video. Let's get started. So we have two major key contributions in this paper. First off is we take in raw video sequences, which is nothing but sequence of image frames, and we are able to pre-process it such that we are able to allocate an automated scene classification per frame. So we are able to automatically able to come up with what is a tag corresponding to every single frame. And then from this metadata, we are then able to filter key frames or the important frames that need to be used for fine-tuning of an object detection or a classifier wherever there is an outlier object. For instance, let's consider that it's a nighttime sequence, and all of a sudden you see a pedestrian for the first time. So in these cases, the frames where the pedestrian is located for the first time, those should be allocated as key frames so that they are then hand annotated, and then reused for fine-tuning of object detector modules. This is just one example, but the categorization that we've been able to do has been it's day versus night. Is it good light versus poor lighting? And then is it a city versus does it have more pedestrians? Is it just parked cars? Is it a highway? So these are the categorizations that we've been now able to allocate automatically on a per frame level. Now, the two methods that we were talking about, first off, we've used a rule-based method. So this is like the baseline method. So what this rule-based method does is it takes these input sequences and then it passes it through very basic object detectors. So in this case, it could be like a YOLO V3. And once the objects have been detected, we then evaluate a few metrics that tell us about the uncertainty in the images. And based off of these metrics, we put them together. We also create an uncertainty peak detector in order to figure out what are the key frames. So ideally, images that have very high uncertainty in them. And so those are the ones that need further fine-tuning. The second one is the SimCLR based model. So this is a contrastive learning approach in order to classify the frames by clustering the pattern. So again, what we do in this case is, first off, you have this whole video frame sequence. But here, the first task is to eliminate the frames that are very similar to one another. Now think about it. If you have a 30 frames per second frame rate, subsequent frames will be very similar to one another. So that's the reason why we have a structural similarity based method to eliminate the frames that are very subsequent to one another. And then we pass it through a SimCLR module. And in the SimCLR module, we are able to extract 2048 dimensional representation, which is a deep learning representation of every single frame. And then what we do is we plot these frames as in the sample space, and we look at the underlying clustering pattern. And here the semi-supervised nature of the algorithm works by we pick only less than 20% of the total number of images in the video sequences to apply label propagation. And once label propagation is applied, we check how accurate is the label propagation in order to categorize every single frame as daylight, or the category of the scene, if it's pedestrian, or if it is parked cars versus is it urban or not. So let's take a look at the first method, which is the rule-based or the spatiotemporal method that we are calling as the baseline. Just as you can see, this is an example from the JAD 025, which is a day poor light and city. Of course, it was a rainy day, so that's why it's a poor lighting situation. In this case, the metrics that we track, first off, we take a look at the background. And again, it's a very simple, spatial, feature detection method in order to extract the background. And in this case, we are very easily able to say if it's day versus night, just based off of the pixel value. Then we take a look at the number of persons in the image that are detected, and we also take a look at the number of cars. So cars, trucks, trains, any of the vehicles. We take a look at all of them together, and then we find the distribution of probabilities of objects in this particular frame. So for every single frame, if you will see that again the objects that you are very sure of, they will have very high probabilities like 0.9, 0.8. But the ones that you're not sure of, maybe they are very far away or because it's just poor quality, their probability will be much low. So you only take a look at all the objects that have probabilities of an objectness 0.2 or more. And in this case, we are modeling uncertainty as the ratio between the standard deviation of all these probabilities divided by the median value of these probabilities. So in a way, and if the uncertainty is high, that means there will be a very high standard deviation. All of a sudden, you will see a peak in your probability of your objects, and then your median value will be also small. So high uncertainty means all of a sudden there has been a change in the number of objects or the probability of finding objects in a particular image. So these two would be the plots of these metrics altogether. So in this one, in the left hand side, if we take a look at the person, so the number of people, if you are seeing that this is the black line versus the blue line is tracking the number of vehicles. And in this case, in the right hand side, we are taking a look at if it's a nighttime or daytime. So here it is a very clear indicator that this is a daytime image. And here the uncertainty is being tracked. So this uncertainty quantity per frame is being tracked by these by the red lines. And again, the average value of the uncertainty or your median value, that is actually plotted in blue. So very clearly it is obvious that these images that are clearly they are shooting far away, that are very high standard deviation from your median value, they are the ones that require further attention. And that's the reason why these would be the images that would be then extracted for filtered as keyframes that would be then used for fine-tuning. So in this case, we are just modeling uncertainty in images based off of the probabilities of objectness in them. Next, we take a look at the SimCLR based model. So the SimCLR based model is again contrastive learning approach. So what happens in it is you take the original image along with some transformed versions of them, and these transformations are very standard. They are either darkened versions, or they are they are cropped versions. They can be angularly. You can have them rotated as well. So you take the original image along with the transformed versions of them, and then there is an automated encoder that goes into it, and then finally it goes through the once you are able to decode it, it comes off as a decoded vectors, and this is the vector which is 2048 corresponding to every single image. So essentially you are trying to figure out that if you have one image and its augmented structure and another image and its augmented structure, the goal is for you to figure out is how similar or how dissimilar both of these images are to one another. So in this case, you're using a similarity-based metric for the final vectors in order to see if the final outcomes or the final vectors are similar or not. So that's the reason why we are combining this particular model along with the images that have different structural similarity, and then what we apply is label propagation, so that we can figure out the clustering nature in the underlying distribution altogether. Now let's look at the final results. So first off, we take a look at the performance of scene classification using the proposed method. However, we see a variation as soon as we start training on one data set and testing on another. So it's like an ablation study. So if you train on Kitty and test on JAD versus train on JAD and test on Kitty, in both cases you will see that the rule-based method is actually more stable across both methods. So if your goal is really to fine-tune an object detection algorithm for outdoor images, in this cases using the rule-based method will be a better mechanism than using the SimCLR based method altogether. And finally, we take a look at the image filtering results. And using the SimCLR methods, we actually find the images that lie at the decision boundary or the cluster boundaries, in which case using both methods, we are able to find or a percentage of filtered frames. So here you see, using both methods, you are able to now extract a very small percentage of frames that really need fine tuning. And we have qualitatively checked them as well, as they become the images where a pedestrian first appears, or sequences that look like city images but are actually just parked cars. So ideally, you would get a false classification in an image like this just because it might look like it's a freeway, but it's actually not. So all images, sequences that have shadows or that they can be false detections, they actually get you'll be able to very quickly catch them using the rule based and the SimCLR based methods. The first things that I am going to be providing through the GitHub is the annotations. So it's called the JAD manual annotations. And if we quickly take a look at the annotations that I have done in this case, it's for every single video frame, from the JAD data set that I've been using. It has been annotated if it's a day, is it a night, and if there are shadows. And if what kind of category does it belong to? Is it city? Is it a freeway? Is it rural? Or is it pedestrian? Does it have only pedestrians? Or if it's a combination, then it's a city. Otherwise, if it's freeway, that means it's only cars, and rural, that means it does not have pedestrians or cars. And I've done the same for the Kitty dataset as well, just for the top 20 training images. Now let's take a look at the code that I've built for this purpose. So the first one, it's called ST scene category. One thing that I will mention is for this whole algorithm, it has been built on TensorFlow 2.7. Currently, the version is actually 2.9 and more for if you're using Colab. So please ensure that you have TensorFlow at least 2.7 or 2.8. But if it's to 2.9 and up, then you should downgrade it. So that's what the first few lines it's doing. So ensuring that you have TensorFlow 2.7 installed. And then we are just getting some of the utilities installed. Now, what we are doing here is for every single frame, we are going to be applying an object detector to the image. And what it does is it detects how many objects get detected per image. Now, in this case, we are going to be using the COCO 2017 annotations. And in this case, there are about 80 categories. So the top 7, the category 0 to 7, those are the ones corresponding to your car and pedestrians and bicyclists and things that you see in your in the outdoor images. So that's exactly what we are doing initially, is to make sure your COCO, your MS COCO and its and its annotations are set up. Once that is done, we are going to be installing these object detection utils. So all of this is very much all of this code is motivated by the TensorFlow hub. So please check out the TensorFlow hub if you want to look into standard object detectors. So this is what we are getting the MS COCO annotation labels getting installed. So what I did here is we started with the faster RCNN object detector. You can use the YOLO, you can use SSD, or any other object detector that you may be interested in. So in this case, I just started with a two-shot faster RCNN model. And once I've detected that, what the next thing what we do is we go to a particular video. So video, all of the images, parsed images in this video. And then what we do is, this is exactly what we are doing. So for every image, we pass it through an object detector, and then we count the number of people or persons or the bicycles. These are your, for your Coco, these are the object labels 1 and 2. And for vehicles, it's actually object labels 3, 4, 6, 7, 8, which correspond to car, van, bus, truck, and train. Right? And then we also find the probability of objectness. So for every single bounding box, there is also a probability of object. So we find the median probability of objectness. And in this case, we find the uncertainty for objectness is the standard deviation over this median value. This is just as it is explained in the paper. So these are all these metrics that we start to, predicting. So if I just take a nighttime sequence, this is what the outcome would look like. So you see all of the cars along with the percentages it's shown. So in this case, this is going to detect that there is 0 humans, 0 pedestrians, and 0 bicyclists, but there are several car instances in this cases, and also the median probability and the standard deviation over median is going to get detected for this particular image. So this is automatically going to tell you, is the uncertainties is going to tell you that, is this a keyframe or not? Is this something that you need to further annotate or not? So that's exactly what we are going to be doing. So for background detection, there is a separate, filter-based method that you should be using. But this is the I'm just explaining the code to you. So if you just figure out this uncertainty score, so first off is for this whole sequence, which is 0024, which is a nighttime sequence. Here you see this is the number of persons. So you see there are just one to maximum 2 people that get detected for this whole frame. And then you see the number of vehicles can actually jump around quite a lot. But then if we start to take a look at this uncertainty, which is your standard deviation over your median value, and then if we find like a 10 window average. So in this case, what we are doing is we are finding a 10-step averaged value of this uncertainty, which is becoming my mean value. So this blue line is actually my mean value. So you see in the instances or in the frames that the red lines or the actual uncertainty is much different. It is over 1 standard deviation away from this median value. Those are the ones where the uncertainty of an object is very high. And whenever an objectness, uncertainty is very high, you should, use that or you should separate that particular frame and use it for further analysis. So such a frame should be re-annotated and used for fine-tuning this object detector. So maybe in this case you need to fine-tune it for pedestrians at night time, right? So ideally, if it would be the first frame where the pedestrian just jumps in, then those frames would have very high uncertainty in the objectness, and that's the reason why. So those frames would now get extracted out. So it is just a standard peak identifier for this uncertainty. And this is the function that is used in order to figure out what is the category corresponding to. So how do you predict automatically, just based off of the number of objects that you're detecting per frame, can you predict what is the category of video it is? So that's what it's showing, that in this case, just for this example, you will see for all of the categories, it is getting predicted as a nighttime city image. The next code that I have used in this paper, it is called the keyframe SimCLR classification. And this is actually using the already pre-built SimCLR. So it is the contrastive learning representation, paper that already exists. So what I'm doing here is, again, this, like you saw, the previous version, the baseline version, it didn't need any annotations at all, right? So because it was just focusing on, pre-built object detection modules, it did not need any annotations to begin. But the SimCLR approach, it does require, because it's a semi-supervised label propagation method, it requires some frames or some images to learn from. So that's the reason why we are starting with some training frames, okay? And again, the training frames and the test frames are completely different. So this is what we are doing. We're just reading the frames first off. And then we prepare the images so that they can be fed into, contrastive learning. So SimCLR. So how SimCLR works, it takes pairs of image. So it may be taking one image along with the zoomed in version of the same image, or one image with with the rotated version of the same image, and then another image and the cropped version or zoomed version of the other image. So
So at input, it's going to take 4 images. So one image along with its augmented form and another image along with its augmented form. And the goal is the final vector representation for every single image is going to say that it is similar to its own augmented form and dissimilar to the other image and their augmentations, right? So in this case, let's take a look at what these encodings would mean. So first off, if you see 00 city, so 00 city actually it refers to video frames that are daytime. So this for the first space is for nighttime versus daytime indicator. So this says it's daytime. Does it have shadows or not? The answer is no. So it is good daytime image, and it is a city. These are city frames. Same way, if you have 00 pedestrians, that means it is daytime. It has no shadows and it has only pedestrians in them. If it's 01 city, that means again it's daytime. It has shadows and again it's a city image. Or if it is 01 pedestrians, again it is daytime. It has shadows and has pedestrians in it. Or it is 10 city, that means it is nighttime. It doesn't have shadows and it's a city. So these are the different categories corresponding to the training set of JAD images that we've used. And here, this is where we are, we are calling the SimCLR model. Again, this is a pre-trained model in order to just come up with its representation, the optimal representations, which are of size 2048. So the vectors, the representation vectors for every single image, it is of dimension 2048 per image. So that's exactly what we are training here. And again, we can say that as the epochs go, the training accuracy keeps improving. So the final, final 2048 dimensional vector, finally we apply, PCA or TSNE. Ideally, you need to do some, dimensionality reduction on that as well. So that's exactly what we do once every single, representation is obtained. And then after that, we apply label propagation. This concludes what we have learned from the paper. I hope you find this code and the data useful and you apply it in order to reduce the amount of manual effort required to train object detectors specifically for specific use cases like pedestrians at nighttime or only car detector, right, or only truck detector, some things like that. So if you're creating something like that, I highly encourage you utilize this code base in order to make sure that your manual effort on labeling or identifying images that should be labeled is minimized as much as possible. So thank you for joining me today and look forward to seeing you again next time.